Okay, so I want to talk about the first half of my thesis work. Uh, the title I've given into it is The Boundary of Symmetric Spaces and Discrete Subgroup of Asymmetric Group Acting, so as a symmetric group of the symmetric space acting on it. So the main objects of study are globally symmetric spaces of non-compact type. Um, we can work with the irreducible ones. Every globally symmetric space of non-compact type is a product of irreducible symmetric spaces of non-compact type. And they always have a so irreducible ones have a almost simple Lie group as isometric group. Almost simple just means it has discrete. Every normal subgroup is discrete. Um, that's, I mean, it could have a actual normal subgroup like center might not be trivial. That's why I'm calling it a almost simple Lie group. Um, and there is a one-to-one correspondence between these objects. If I take a almost simple Lie group and its maximal compact subgroup, then G quotient K, I can put a G quotient K is a homogeneous manifold. I can put a Riemann metric there such that it will become a irreducible symmetric space of non-compact type. Um, and for example, a real hyperbolic space has its isometry group to be this matrix group, this group of orthogonal matrices which preserves the 1n product, 1n bilinear form, non-linear bilinear form, symmetric non-linear bilinear form. And we wish to study the geometric properties of this symmetric spaces and its quotient, and using Lie theoretic facts about the groups, its Lie algebra, or its subgroups, and vice versa. We can prove group theoretic facts about these groups and subgroups by using the geometric properties of um, spaces and its quotient. Now, we want to use the form. We don't want to use the general strategy because we'll have to prove general theorems about them too, and that will be a lot of prerequisites. We want to just work with submanifolds of PNR. So PNR is a sort of all symmetric positive determinant matrices, um, which is an open set in the vector space of symmetric matrices, and we can identify. So it's an open set of subset of a vector space. So I can identify tangent spaces using with the vector space itself, and using that identification, I will give it an inner product which looks like this for each p in the open set. This defines a Riemann metric, and using this Riemann metric, we can with this Riemann metric we can show it's a cat zero symmetric space. So it's a complete Riemann metric, and we can show its curvature is less than equal to 0. Equivalently, it's a simply connected, and also is simply connected. Equivalently, it's cat 0, and it's also a symmetric space. Uh, the symmetry at identity is precisely P going to P inverse. Positive identified matrices, the inverse of a positive identified matrix will also be positive identified. So yeah, that's that, and it's also homogeneous. That is coming from by this. GLNR acts on this PNR by this transvections. TGP takes TG takes P to GP DG transpose, and these are isometries. This is precisely the inner product which will take the inner product of P is good identity to the one at P. And these transvections are isometries under this inner product, and the stabilizer of this action is this is a transitive action. We can show T root P takes identity to P, where root P is the so G is equal to root P for that case. Root P is the unique positive square root of a positive defined matrix. We can show that that exists using diagonalization or um, general theory. And on the group theoretic side, so PNR is a symmetric space. It's not on non-compact type, but it's at 0. And the group it comes with is GLNR. And GLNR has this order to automorphism, which is given by G inverse T, which is related to the symmetry. G going to G inverse, P going to P inverse is literally the symmetry or identity. And so this is the order 2 automorphism, because inverse is order 2, transpose order 2, none of them are group automorphisms, but both of them combined will give you a automorphism, a group automorphism, and it's a order 2. And that induces this Lie algebra automorphism, which is x going to minus x transpose. And because it is a linear map of order 2, it is diagonalizable. And the plus 1 eigenvalue and the minus 1 eigenvalue are precisely SONR. So antisymmetric matrices plus symmetric matrices. We know that decomposition exists in all of a set of all matrices, but it's of all matrices. But this is precisely the diagonal components of this linear map, eigenspaces of this linear map. And this structure will generalize to submanifolds of PNR. So we wish to study completely geodesic submanifolds of PNR, and they will be cat 0. So PNR is cat 0 symmetric space. The completely geodesic submanifolds will also be symmetric space. Completely geodesic just means it's not just totally geodesic. For every geodesic in the ambient manifold PNR, if it hits the submanifold in 2 points, the entire geodesic line starting from minus infinity plus infinity, that entire line is in the submanifold. That's what completely geodesic means. We will construct them from by considering subgroups of GLNR. So take a closed subgroup of GLNR, which is closed on a transpose of matrices, and it's also another condition which needed for the um, completely geodesic part, which is just, I call it exponentially closed. You just have a exponential of x in G implies exponential of Tx in G. That condition is needed, but for not all x, you just need that to be satisfied for a symmetric matrix. So if a exponential of a symmetric matrix is in G, then the entire exponential of the entire line spanned by x is also in G. And if I consider groups like that, then orbit of G, orbit of I in PNR, so this GLNR acts on P, so G acts on P, and I take the orbit of G, uh, orbit of I under G, then that will be a completely geodesic closed and embedded submanifold, and which will, of course, this is cat 0 and symmetric space. So any completely geodesic submanifold of a cat 0 symmetric space is also cat 0 symmetric space. So this will also be a 0 symmetric space. The converse is also true, that if I start with a completely geodesic closed embedded submanifold, which will be a cat 0 symmetric space, and I consider this group which preserves, so these are all elements of G which transposition preserves this submanifold, then it will be T closed, transpose closed, and exponentially closed subgroup. It will be also a closed subgroup such that the orbit is precisely this X. So there's a one-to-one correspondence in some sense. But there might be some subgroups smaller than G which also have the same orbit. So this is not exactly giving you the same group back, but yeah, there is a one-to-one correspondence. I guess with the large, so there can be more groups on the left, but you can take the largest of all of them. So this is G is taking the largest of all of them. Now this is a setup. Now we wish to study stuff flats inside the outer space, and they will correspond to some Lie theoretic objects inside the Lie group of the Lie algebra of G. Now, how do you construct? So what is P here? If I take the Lie group, so my setup is this: there is a T closed, exponentially closed subgroup of G, and I look at the corresponding X, which is orbit of I. Now I take Lie algebra of G, which is a tangent space identity. This is a matrix group, and this linear evolution is diagonalizable. So it decomposes the entire thing into some k plus p. Some k will be Lie algebra. P will be just a vector space, vector subspace. And I can consider abelian subspaces of P. Abelian subspace as in it will be Lie algebra, so it will just be the trivial Lie algebra inside P, but P is not a Lie algebra. So we will consider subspaces of P, which is a trivial Lie algebra. So every bracket commutes inside it, and we can show that there is a one-to-one correspondence between these subspaces and flats containing identity. So given its transitive, any flat I can map it in such a way that it contains identity. So that will be, if there are flats, there all will be flats which contain identity. So that just means it's a distance isometric to Rn, and that means, for example, geodesics are minimal geodesics, unit speed geodesics are flat. So one-dimensional flats always exist. Now, if you take the set of all flats containing identity, they will correspond to um, subspaces, and the correspondence is by exponential. You take a abelian subspace and you take it exponential. So exponential, uh, so p exponential of p will be all of x. That is also the case. And exponential of b will be a flat here. For example, exponential of tx will be a geodesic. It is so that dimension also matches up. The dimension of the flat and the dimension of the subspace. Rank of a space, Cat0 symmetric space like that, is the dimension of its maximal flat. So maximal flats exist because maximal abelian subspaces exist. Because P is finite dimensional. You can also do the same thing for flats. One-dimensional flat exists, and the dimension of X is finite, so maximal flats exist. And rank is the dimension of one of his maximal flat. To show that this is well defined, I have to show that all of the maximal flats are of same dimension, which is true. Now, we want to consider the boundary of this Cat0 symmetric space. So boundary of any Cat0 manifold or Cat0 metric space is the same definition. I will consider geodesic rays starting from any point with up to equivalence, up to circle asymptotic geodesics, asymptotic equivalence classes, and which just means it's bound. Distance between two of them, two geodesics is bounded, if not if they're equivalent. Uh, Now we can put a topology on X union the boundary, which is called the cone topology. There will be multiple topologies put on the boundary. This is the first of them, cone topology. This makes the CAD 0 D1 manifold. Um, so X bar homeomorphic to Sn. So the boundary will be, sorry, X bar will be the closed wall, the boundary will be Sn minus 1. Um, and isometries of X will extend to X bar as homeomorphisms. And given a boundary, we can define more objects because the isometric group now acts on the boundary as well. And that action is what we will use to prove relevant theorems. For example, we get, on the left hand side, we get a subgroup, which is stabilizer of a boundary point. So this action will be by homeomorphism, L will be also be continuous. Now we will focus on the rank one case. We'll focus on the case of real hyperbolic space. So real hyperbolic space is a isotropic Riemann manifold because it's frame homogeneous. It's even stronger than isotropic, and so its sectional curvature is constant minus one, and it's by definition cat minus one. Um, and minus one just means I have to compare the triangles here to compare with Rn, Rhn, but I'm talking about Rhn, of course. Trivially, cat minus one metric space, and because it's isotropic, it has to it carries every direction with to every other because it's frame homogeneous. It can't be rank can't be any higher than one. It is carrying flats. Uh, so two-dimensional flat can only be carried to another two-dimensional flat. But um, if that happens, then the curvature will not be minus one. Yeah, that's why the rank is one. Yeah. We can show in other Um, another thing to show you can show this using that is on the fact that totally geodesic submanifolds which are complete in RHN, completely geodesic submanifolds are just are real hyperbolic space of a lower density. Um, Now we can consider a discrete subgroup of the isometric group. So the isometric group of RHN is O plus 1n. This is the entire group. SO1 plus the SO plus is the kinetic component of identity. Now we can take a discrete subgroup. This is a typo. This will be RHN. Um, if I consider a discrete subgroup, now it acts on the entire compactification. And now we can consider objects related to the boundary. So I can define the limit set to be, so if gamma is um, finite, then this doesn't make any sense. But if gamma is infinite, discrete subgroup is infinite, then I can consider its orbit in RHN bar. It's a compact set. The orbit will be, if the orbit is infinite, so then it will have limit points. But it can't have limit points in the interior because it's a proper action. So the limit points need to be on the boundary. So that is where I'm looking at the accumulation points precisely, and that set is called the limit set. And it is true that this set does not depend on the boundary point x. And another number that is correspond coming from this group is like some. Um, so this is the displacement of x under isometry. If I take exponential of minus alpha times the displacement and sum over all elements, it might be, so that it should be, so that this set is less than infinity. This should be less than infinity. If this sum is less than infinity, then this series converges. I will take all that alphas such that this series converges, and I will take the infimum of that. This should be less than infinity. That's a typo. Um, then that number, that infimum, is delta gamma. This series might converge or diverge in this delta. This is called the critical exponent of gamma. These um, objects. So this limit set will give me more information about this gamma, how the gamma acts on the interior of the space. For example, I would know if gamma is co-compact or of finite volume, if the quotient is of finite volume, um, or not, if I study the exponent or the limit sets. They will have information about that. There is a proof of modularity of real hyperbolic manifolds. Um, there are multiple proofs using. There are two proofs using Patterson's measure, but the one I'm considering also uses the ergodic measure for geodesic flow, the real hyperbolic manifold, not RHN, but quotient. Um, so there will be finite volume real hyperbolic manifold for modularity. The ergodic measure for that, which is called the Bowen-Margolin measure, there are multiple ergodic measures, but this is a unique. So this satisfies some property. Um, there's a proof using these two measures of the proof of modularity of real hyperbolic manifolds of finite volume. Uh, we wish to understand that proof and possibly generalize the theory. So maybe we will not be able to prove modularity of um, higher rank symmetric spaces using Pallas-Sullivan measures, or uh, because that, so higher rank will have different properties. They will not be cat minus one. That is the biggest. That cat minus one. So that we use properties of cat minus one spaces to this in this proof. So we can't generalize this proof. The theory might generalize into into the higher rank case. That is what we hope, and we wish to look at that in the next half of the thesis. Thank you. I have added the references I have been following, but these are definitely not complete. Uh, yeah, but they are comprehensive. Definitely.